All right, we've learned about empirical formulas and we've learned about molecular formulas. And so now we want to see how we can figure out the empirical formula for a substance experimentally. Specifically, if we're talking about metal oxides. Now, what is a metal oxide? A metal oxide is basically the substance that's formed whenever you burn a metal, right? So you're taking that metal and you're combining it with the oxygen, and the outcome is a metal oxide, right? So we've got really straightforward steps here. I've outlined them. I don't think the book has this in it, but it's just something, these are the steps that we're going to go through, and this is always the way that you do it when you're figuring out the empirical formula of a metal oxide. All right, now a metal oxide is going to be ionic, okay? And so for the ionic formulas, for these guys, this will always work. So we're just going to do example 8.3 in the book and see how we would apply these 4 steps here. And that particular problem says a chemist is burning 15 grams of zinc in excess oxygen. So we know that we're forming a metal oxide because we're combining a metal, zinc, with oxygen, right? And the result, we start with 15 grams. The result is 18.7 grams of a white powder. So we're taking this 15 grams of zinc, and we're going to combine it with oxygen to burn it, right? And the outcome is going to be this zinc oxide. We don't know how much zinc, we don't know how much oxygen, but what we do know is that we produce 18.7 grams of this stuff, and we know that we started with 15.0 grams of zinc, the problem tells us. And so the question is, what is the empirical formula for the product? All right. Now, one thing we do know, because this substance here is 18.7 grams, and we started off with 15 grams, we know that we must have 3.7 grams of oxygen, right? That was contributed to the formation of this zinc oxide, because mass has to be conserved. So 15 plus 3.7 equals the 18.7 grams. So that's important for us to understand, that that's the mass of our oxygen. And so we've already really done the first 2 steps here, right? We've measured the mass of the metal before burning, right? That's the 15 grams that they've gave us. And we've measured the mass of the substance after burning. That's the 18.7 grams that they gave us. Also, we've done this step, right? We've taken the mass afterwards, the 18.7, subtracted from it the mass before, and that's given us the mass of the oxygen. So we've determined that as well. Now, we have to use the number of moles. We can't use grams to figure out what the empirical formula is. So this is really important. Notice here, we're using the molar mass to calculate the number of moles of the metal and the number of moles of the oxygen. So let's do that. We're going to go to our periodic table, and we're going to look up the atomic mass of zinc. And when I do that, I get a value of 65.38. Now that's the mass in AMU, right? The atomic mass in AMU, but it's also the molar mass. It is the number of grams per mole, right? If you had a if you had a mole of zinc atoms, it would be 65.38 grams, right? And so we're going to do the same for oxygen. When we look up oxygen, oxygen has an atomic mass of 16.00 grams, which means that its molar mass, if we had 1 mole of oxygen, it would be 16 grams as well. Now, this is important. The oxygen here is O2, right? But the oxygen over here is not O2. And so that's why we didn't find the molar mass of O2 here. It's because we're trying to figure out the empirical formula for this guy. And in this case, it's not all by itself. Oxygen is not a homonuclear diatomic in this particular formula here. So we're going to leave it as 16 grams. A single oxygen atom has a molar mass of 16 grams. And so when we calculate the number of moles then that we must have over here, we find out that we have 15. We start off with 15 grams of zinc, right? We multiply that times the molar mass, which says 1 mole of zinc is equal to 65.38 grams of zinc. And doing the math for that, we get 0.229 moles of zinc. All right. That's how many moles of zinc we have right here. All right. Why? Well, because that was the moles of zinc we had over here. All right. The moles, the number of zinc atoms don't change, right? Also, on the other side of the equation, we had 33.7 grams of oxygen. And we know that 1 mole of oxygen is equal to 16 grams of oxygen. And so doing the math with that, we have 0.23 moles of oxygen, right? That's the number of moles of oxygen we have over here. So we've done step number 3 now, right? We've figured out the number of moles of each of those guys. So the last thing we need to do is divide the moles of metal by the moles of oxygen to get the ratio. And so that tells us, when we do that, the moles of the metal is 0.229 moles, and of zinc, right, divided by the moles of oxygen, 0.23 moles of oxygen. And when we do that calculation, we get that there is 1 oxygen, 1 zinc per oxygen, right? Moles is going to cancel out here. So what we're left with is zinc over oxygen. And so what this tells us is that for every 1 zinc, there's a 1-to-1 comparison between, 1-to-1 ratio between zinc and oxygen. All right. So for every 1 zinc atom, there's also going to be 1 oxygen atom. And so then the formula for this guy is simply zinc 1, oxygen 1. But of course, we never put the 1s there, right? So we would just write that as ZnO. And that would be our empirical formula for the zinc oxide. Okay, so that's the empirical formula specifically for metal oxides, how to find that experimentally. Next video, we're going to figure out how to determine the empirical formula of substances other than metal oxides. All right, so stay tuned for that.